Carolyn Margolin. I am the director of the STEM Isle grant. Who here is being paid by STEM Isle? A few of you know. Okay. If you don't know who's paying your stipend, please check. You should know where the money's coming from. It becomes very important when it comes time for your presentations and your posters. You do not want to thank the wrong grant or not thank the right one. It has happened. It's not good when it happens. So please check. On my left, we have the very intelligent and handsome Dr. Travis Craddock from Nova Southeastern University, who here is working with Dr. Craddock. He is one of our SRI mentors, and he has been kind enough to come and give our statistics presentation for the last several years. So if we are all signed in and ready to go, I'm going to turn the podium, desk, computer over to Dr. Craddock. Please give him your undivided attention, learn lots of good information because you will need it for your presentations.
Thank you very much, Dr. Margolin. Okay, so we'll come back to this in a minute. Hopefully you guys have signed in and got yourself an account on Code School there for TriArc. Okay, so this is the Introduction to Research Data Analysis workshop. My name is Travis Craddock. I am an assistant professor in psychology and neuroscience, computer science, and clinical immunology up at Nova Southeastern University, and I hold a degree in physics. So I'm kind of at a weird intersection. I use physics and math skills in computer simulations to try and find cures for complex chronic illnesses involving brain inflammation. So it's really at the intersection of everything here. What I'm going to talk to you guys about today is research data. What is research data? How do we analyze it? And specifically, I'd like to focus on the kind of stuff that you guys are going to deal with in the future. It's not just regular research data, but it's going to be big data. Okay, so large data sets, complex data sets with lots and lots of values. Okay, so first off, what is data? Okay, so data is any information, facts, statistics, and it's primarily broken into two categories. Okay, there's quantitative data, which is stuff that you measure. How fast are you going? How tall are you? How heavy are you? How much money do you have in your bank? How little money do you have in your bank? Anything that you can assign a number to is quantitative data. That includes things like psychological measures. So if there's a scale such that you go and it's a little bit subjective, but you can put on a scale of 1 to 10. How well do you feel today? How happy are you today? I'm a 6. Okay? Maybe after this class you'll be a 4. That's still quantitative. Okay? Qualitative is the other type of data. It's something that doesn't have a value associated with it. So what is the color of his shirt? Oh, it's red. Well, how red is it? Well, you can't really give it a number. It's either red or it's not. It can be, according to my wife, there's many colors of red. For me, there's one. But regardless, you can't assign a number to it, okay? It's just a quality. It's something descriptive. Something, basically, you could think about it as something subjective. Something you can comment on, but you really can't ascribe a value to. Now, both of these are data. Both of them are used all over the place in science, in marketing, in finance, and whatnot, including qualitative data. Don't underestimate qualitative data. Now, research data, the data that we specifically want to talk about as research scientists, is any data that you collect primarily for the purpose of analyzing to produce a new original result. So it's not just collecting data. Oh, I have $10 in my bank. Okay, so that's data. Okay, but if I take that and I analyze it with some other numbers to find it, well, how did I get to $10 and how do I get more? I will all of a sudden produce a new research result that will allow me to get new money in my bank, or something along those lines. If you analyze it to solve a problem or to give you new information that wasn't there before, that's what's known as research data. Now, what I want to specifically talk about is big data, because we live in the age now of computer science, computer technology, more and more data. Okay, so currently, as you guys are sitting there on your iPhones and on the web, your internet service provider is now collecting data on you and what you're looking at, what you're retrieving, how much data are you using, what are you looking at on Amazon, what are you watching on Netflix, how much money does this person? Well, they can't look at what's in your bank, but your financial institutions can look at that. There's medical records. Everything in clinic now is moving from old pencil and paper, well, maybe not pencil, but pen and paper charts, and they're trying to move that into e-charts. Okay, so these electronic charts that are specific to you, that at some point if you move from one healthcare practitioner to another, they can just transfer that file and they have your whole medical history there. So everything is moving over to this large sets of data that are describing individuals, that are describing phenomena out in the workplace, out in the environment. Things like social networks, connections between people on Facebook and Twitter, who's talking to who. Not so much right now are they analyzing the content, but there are programs that can analyze the language and everything that you're using. What are you saying? What are the key terms that you're looking at? Things like the NSA, you guys are quite familiar with that down here. Business systems, so medical records, bank records, stocks, okay? Financial records, shopping information, marketing. So what's coming out new and more, you'll start hearing about this, is the Internet of Things. So your cars now have connection to the internet. So there's GPS, but then there's also connection to the internet through your car or your home or security. A friend of mine bought a house and he has a thermostat, this Nest thing that's connected to the internet. So if he's out, and he's going to be late, he can program his thermostat to warm up, and so he can save some money, or he can cool it down when he's on his way home. I was at Home Depot the other day and there was a fridge with a gigantic iPhone in the front of it, and you can be out at the club or something and look, how much milk do I have left in my fridge? I don't know why you would want to do that, but these are the things that people are inventing. They're coming along, and every single bit of this is recording data. Now specifically what I'm going to talk about, because you guys may be budding scientists or have interest in science, is what's particularly health science. I mean, you're collecting large amounts of data for other things, but in health science there's this thing called omics. Okay, who here has heard about omics in some regard? Like genomics, proteomics, transcriptomics, metabolomics, okay. So what this is before, what someone would do would be like, I'm interested in gene A. Okay, so gene is something in your body that controls how your body works. So before, what they used to do is they would have this special probe. So they would collect some of your blood and put the blood on the probe, and then they would be able to measure that one gene. And they would be like, look at what this one biological molecule is doing. Now what they do is they have a chip that analyzes 54,000 genes all at once. So they put one drop of your blood, and now they can measure all the genes in the human genome on that one chip. Okay, so that's for genomics. They do the same thing with measuring your protein, with measuring your metabolism, with measuring transcripts, which are other things in biology. And so as we measure things in science now, it's not just one individual measure or a few measures that we're getting all at once, but we're getting literally tens and hundreds of thousands of measures continuously. And these things are set up on machines, so they're constantly being upgraded. You have large amounts of data. Miley, who works with Zeus and I up in my lab, today she was looking at gene expression data, and there's 54,000 entries of measures and about 100 patients. Okay, so for each of the patients, there's 54,000 measures, and I said I want you to look for patterns within that data. And so that's the kind of stuff that she's working on. So one of the quotes that I keep saying, and this quote is about 5 to 10 years old now, is that in 1 year now, more data is collected than has been gathered in scientific history to this point. Okay, so that's the speed at which this is gaining. So we're gathering lots and lots of data, and then we're storing these things in massive databases and Google massive centers and whatnot. But in order to understand it, we need people to come along and do some sort of research data analysis on this. We gotta make sense of it. Otherwise it's just a bunch of numbers, okay? Now, for the most part, you guys will deal with some aspect of this in your careers, whether it's financial, health, pure science, or whatnot. I mean, if you're gonna be going into any sort of quantitative STEM type field, you're gonna be analyzing data. And depending on the size of it or the shape of it, will determine whether it's big or medium or small or specific or whatnot. Now there's multiple tools that we can use, and what you may be most familiar with is Excel. So Excel is a spreadsheet program. Who here has to use Excel every once in a while? Okay. Who here hates Excel, by the way? Okay, so Excel is a spreadsheet program that you can use to analyze sets of data. It primarily was initially set up for analyzing financial data. But it can do some statistics. Now you can get into more specific programs and software such as SPSS and SAS and Minitab. These are all programs specifically for analyzing statistics, so doing your t-tests, for doing comparisons, getting the average of things, the mean, the variance, these types of terms that you kind of hear in stats class and they just kind of blow by. They have programs, so normally, and correct me if I'm wrong, in class they teach you how to do it the long way and you actually have to calculate it out. These programs are set up such that you don't have to do that laborious task anymore. Okay, so you just have to know how to program it and then it can do it on reams and reams of data all at once. MATLAB is something that Zeus is using a lot in my lab, but specifically we're going to be talking about a program called R. R is just a coding language, and that's primarily when you're dealing with large sets of data, you're going to need to use some sort of software. And with any sort of software, whether it's Excel, MATLAB, R, there's going to be some sort of syntax, which is just the way to tell the computer what you want it to do. And it never looks pretty, okay? It's never just point and click. It's always, you have to kind of put in some esoteric code and to get it to manipulate the data in some way. So I want to expose that to you today. So we're going to do a little bit of a tutorial in R, just to get you guys a feel of what it means to start to handle data and work with data. So this is where I want you to go to that Try R Code School website. If you haven't created an account, create an account. If you have, start doing chapter 1. Okay, so we'll take the next 15 minutes and start going through that first chapter. Okay, and I'll wander around just to make sure everyone's on the same page. Okay, does anyone here have problems getting to the website? If you guys have problems, just raise your hand, I'll come help you out.
Chapter 1, where do we find them? Let's find it.
Let me take a peek. Okay, so where's this code school there?
Yeah,
Get rid of learn and take courses.
You gotta go to that link right there. Yeah, it says like codeschool.com.
Courses and then /try dash R. Yeah, and then dash R. There you go there, and there's chapter 1, there's level 1, I guess. Yep, and you can just click on number 1 and you should be able to just free, so they're all in there. Maybe you can click on where it says free or using R. Oh, here, play course for free. Try that. There you go. So then you go to R syntax. Yes. Yeah. So number 1 is with chapter 1, and just do chapter 1 right now. Yes. Yes. Yeah. So this is number 1. It's trying to teach you how to represent the numbers and everything. So just follow along. Yes, okay? Yeah. Okay, so, click that, and then just hit play course. Yeah, you gotta rewrite it. No, you don't have to plan this. Like, it just... Okay, so if you change something slightly, then the computer can't recognize it, and it doesn't do what it's supposed to do. If you talk to anyone, you can talk to Zeus up here, that as you build large scripts, so you can write all these commands out and put them in a pattern such that they'll run over and over and over again. But if you miss one small thing in there, maybe you put a semicolon as opposed to a colon, then it ruins the whole program, and sometimes you spend hours trying to go through it to figure out what you did wrong. Okay? So that's the bane of coders, but once you get around that, you can start to see what the power of these processes are. Okay, so that's the syntax of the coding. Now, if you haven't finished yet, why don't you can just keep working along and listening as I talk here. Okay, so basic data analysis is a process. It's not one thing. It's not one specific thing. It's a process that you have to go through every time you're dealing with data. Okay, so the main thing first is, in order to do anything, you have to collect data. So the number one thing in any sort of research experiment or any sort of research data is you have to go get the data to begin with. What's your start input data? So you go out to the world, you gather data, and then you bring it home, and now what are you going to do with it? So the next thing you're going to do is you have to inspect it. Did I get all the data that I needed? Is it in the right form? Do I have the right units? Did I measure what I was supposed to measure? Then you have to clean it, okay? Anything that you're missing, you got to make sure that you put it in the right spot. You got to make sure that it's in the right format, because that syntax stuff, that stuff can really mess up your program or can mess up your process. So you got to make sure everything's in the right column. You got to make sure everything is to the right unit. You got to make sure everything has the right number of significant digits, that kind of stuff. Then once you've got the data and you've processed it, you can get what's called a clean data set. And once you have this clean data set, you can start to do stuff with it. So usually the first thing you do is you don't want to have to go out to the world and collect all of your data, every single bit of data, and then bring it home and process all of it. What you'll do is you'll take a small subset of it when it's first coming in, you'll clean it, and you'll do a little bit of preliminary analysis on it. So you know, let's say you're trying to analyze financial data to say that you're trying to check to see if women and men earn the same amount in the workplace. So you gather a little bit of data from some people that you know at the company, some men, some women, and you do a comparison, some statistics between the two, and you find out, well, no, that's not the case. Okay? So if that's the case, then you have to go back, okay, and then start to collect more data. Or you might find, well, this isn't really the right way to analyze the data. We should analyze it a different way. So at first you do a little bit of exploratory data analysis. And if that exploratory data analysis is promising, you can move on to build models and algorithms to analyze all of the data. You can try and make predictions about what the data says. You can try and find results about what the data says. But if that exploratory data analysis tells you we don't have enough data yet, or we need more data, or we need a different type of data that we didn't measure in order to answer our problem, then you have to go back down over here to where the data is processed and then reprocess it. So for example, maybe you're measuring the speed of cars as they pass a given intersection because you're working in some sort of traffic division of the government, okay? And you collect it all. And one person that you're working with is a Canadian, and he's measuring everything in kilometers per hour. And the other people are Americans, and they're measuring everything in miles per hour. And you get there, and you go to analyze it, and you do your exploratory data analysis, and you're like, oh, the Canadian guy screwed up. So you gotta go back and reprocess the data to get a new clean data set, okay? And then you can go and you can keep checking it out, okay? And so there's this iterative type processing that goes on to make sure that, is the data telling us the kind of stuff that we need? Do we have everything to solve the problem? And if so, then you can start to build these more complex programs and algorithms to process large amounts of data. And once you have that, you can then get a data product which you can tell to the world, which revolutionizes it. Or you can create some sort of visual report, like a poster, that you can present at some sort of conference, maybe at the end of the semester type thing, and use that information to make certain decisions, maybe policy decisions. If you're analyzing your own financial data, you might decide, maybe I shouldn't keep spending my money on that. And you can make a decision which can better for your life. So these are the basic steps that are that go through a data analysis project. So the first thing you're going to do is you're going to start with a plan. So myself, I do a lot of the data analysis up at the Institute for Neuroimmune Medicine, but I'm doing it on the behalf of clinicians that are dealing with patients. So they're looking at the patients, they're saying, these people are sick, we want to know how to give them a drug or some sort of treatment regimen that can help make them feel better. So the overall idea is we want to make them feel better, but how are we going to do that? So I have to sit down with the clinician and we'll go through the process and define what it is we actually want to do. What does it mean to make them feel better? Well, on that scale of 0 to 10 on your happiness, we want them to be at 10, okay? So you have to determine what is your outcome, what are you trying to figure out. In order to get to that outcome, what kind of data do we need to start with? Okay, so you have to design your experiment and the data collection methods first. So if you're trying to answer a question, you gotta lay out what the question is and decide ahead of time, in order to answer that question, what do I need to know? And then start the process of collecting your data. Don't do it the other way around. If I said, hey, I have something that I want you to solve, you wouldn't go outside and start measuring people's height and weight and then come back and say, look, I have everyone's BMI. And I would say, well, that's really not what I was going to ask you about. I want to ask you about, why is the sky blue? You'd have to go measure different things to figure that out. So you want to design it ahead of time and then stick to that plan. So define your problems, determine what your objectives are, brainstorm to figure out what it is you need to grab, what it is you need to measure, how many things you need to measure, what are things that may be externally affecting your measurements that you also need to take into account, and then design your experiment based on that. And above all else, once you design that experiment, before you even collect the data, once you design it and you know what your experimental method's going to be and what kind of data analysis you're going to do, is stick to your plan. Because a lot of times what will happen is no longer are you going to be in a work environment where it's like you're going to be the person, you're going to be the guy, you're going to be the girl that everyone goes to for one thing. Is that you are going to be working in conjunction with someone else, okay? So you are going to get the data and analyze it, someone else is going to be the one collecting it, and then someone else is going to be the one that's writing the reports about what it means. Something along those lines. Now, if you have a plan, and your job is to analyze it, and then the person who's collecting the data says, well, I couldn't get this data, so I got you this instead. That's not sticking to the plan, okay? There may be external factors that cause you to have to shift things, but for the most part, try and stick to everything, because everything that everyone in the team is working on is based on the plan, and you can't mess with the plan. So once you have your experiment designed, collect according to the design, and keep calm and stick to the plan. Deviation collection will have implications for the original design and the analysis. Okay, so for example, I have a project, a grant-funded project, where I'm looking at Gulf War illness veterans who have prior past traumatic experiences from the war. And I was told that we have data that measures their prior traumatic experience for all of the people we've ever seen. I got the grant, I said, can I have that data please? And they did not have all of that data. So now I'm trying to work my way around to try and figure out a new way to analyze it, because the plan was not stuck to. Okay? The other grants said that they had this data, but they actually didn't collect it. Okay, so sometimes you run into that, but for the most part, try and stick to it. It saves a lot of time and energy.
Fact-driven reporting is important.
Yes. Okay, so now once you've collected the data, you have all the data that you were supposed to collect. Now you have to start analyzing it. Now you have to process it. So you guys looked a little bit at the R program, kind of how to put in a number. You may have done this in Excel, okay, where you can start to put in a group of measures into your Excel spreadsheet. You have to organize it. You don't just put random numbers all over a spreadsheet and expect someone to figure it out. It's not, if you've ever seen my sketch notepads, okay, there's someone's phone number up here, and then there's a little bit of a laundry list and to-do list over here, and then there's a doodle that I was working on when I was doing something, and then a couple numbers, which I usually don't know what they are later on, but they were important at the time, that I've written over here. That's not how you actually want to keep research data. You want it to be nice and organized. Columns and rows, or beyond that, into like three-dimensional structures or so forth. Okay, so things like this, if you put a group of data in a row, that's something that, in a column, that's called a vector. It's got one dimension, okay, up and down. Okay, and then you have your measure that goes with that. So that might be your, if you want to figure out what's the age or the age distribution in the class. Okay, so you go around and you ask everyone what their age is, you put it down, and then you can analyze that column, and that's the only thing that you're worried about. Okay? But what if we want to know what is your height in association with your age? Is there some sort of correlation between height and age? Okay, maybe not so much in this age group, but if you're working in elementary school, then height and age, they correspond with one another. So you may have then a matrix of data. So here is, one individual with their height and age, and maybe their weight, and here's the next individual with their height, age, and weight, and then the third person, the height, age, and weight. So now you can start to include more data in these structures as you make them bigger and more dimensions. So this is only one-dimensional up and down. This is two-dimensional up and down and side to side. Then you get a three-dimensional thing, which is up and down, side to side, and then out of the page type of thing. And you can go to higher and higher groups. So you have to learn how to build these, so you have to put them in your spreadsheets and organize the data in that way. But you also want to make sure that you can analyze data in these forms. And then that's what the next chapter is in R. And it's actually 2 chapters, so go through and do chapter 2 and chapter 3. And I'll tell you how to create those vectors and matrices, as well as how to manipulate them. Maybe how to multiply 2 vectors together, maybe how to multiply a matrix with the vector, and so forth. Okay, so you can start going through and doing that now.
That's what about.
Somewhere, type something in wrong, use the wrong syntax again. 1, that shows you how finicky a computer program can be. It's got to be the exact words that it's looking for. 2, it shows you how easy it is to fat finger something and put in the wrong number when you're entering data. So that's the number 1 thing, entering data to err is human. For the most part, whenever you're trying to build a software program, you want to minimize the amount of human interaction that's going to be involved. One place where you can't get away from that is the initial data. Well, that's not true. Most of the time, it's the initial data collection. You got to have a human in there somewhere. Nowadays, we have things like smart watches that are monitoring your heart rate and pulse and all that kind of stuff, which automatically take the data and they can pass it to a program, which on the internet, which already has a program associated with it, to analyze it automatically. Okay, but at some point, someone had to figure out how the watch worked, and they were collecting data directly. Okay, anytime that there's a human involved, there's always the opportunity for errors to be introduced into the data. So we don't want this for several reasons. So incorrect and inconsistent data can lead to false conclusions. Okay, so if you grossly enter something incorrectly, like I had a colleague who gave me reams of data, gene expression data, which is, like I said, has tens of thousands of entries. We noticed later on after doing some analysis that one of the patients had all of their values which were 10 times less than everybody else. Okay, and that was just because of a division error somewhere along the way. But when we did the analysis, it brought up a whole bunch of things of this group has something very significantly different happening in it compared to this other group. It was all because one person had 10 times lower the value, so it took the average for that one group and dropped it really low. Okay, so that simple error of dividing by 10 where you shouldn't have can cause a problem. It can lead to incorrect results, in false conclusions. Now, this can do many things. It can cost money. So if you go out and you now take those results and use it to start up another study, you can go and you can start looking at the wrong thing. So you've spent money looking at the wrong thing now. Other times it may lead to having to do another analysis. So maybe when you were collecting the data or entering it, you did it in such a way that now you can no longer recover the original data. So you have to go out, spend money to collect new data. So that's the most minor thing though in the long run. I mean, it's a big pain and it might cause you to lose your job if you cost your company a lot of money. But that's the best case scenario. So you lose a bit of money for the company. The other things can be detrimental to society. So for example, there's a lot of hubbub about climate change and whether there is climate change or no climate change. And you'll have some people saying that it's there, some people that are saying that it's not. And they're always pointing back to certain studies that are misleading or controversial. And whatever way you look at it, if climate change is there and we're not addressing it, that's detrimental to our society. If it's not there and we are trying to address it, then we're wasting money, and again, it's detrimental to our society. So in one way, whatever way you go, it's good. A false conclusion can be detrimental to, policy decisions, to how you're going to implement a new technology, which maybe you don't want to get it getting into the wrong hands, that kind of stuff. And finally, it can be fatal. Okay, so a classic example we're always taught about when we're doing pharmacology is if you come up with a treatment. For example, there was a group of engineers who discovered a drug which may be efficacious in some disease. I don't remember what the disease was. Now, the way that engineers work is different from the way that clinicians work. So when engineers set up a clinical trial, the way engineers usually work is they set their upper tolerance and then work their way down. Okay, so find out what the minimum tolerance is. Whereas clinicians, you start with your smallest dose and work your way up. So because they went the opposite way, they started with a dose that was too high and ended up killing people in the experiment. Okay, that's why you always want to, make sure that you're doing the proper analysis, making sure that you have the right numbers to work with, because you could end up costing someone their life in the long run, depending on what you're doing. I mean, if you're doing marketing for Amazon, you might ruin someone's day, but probably not their life. But don't quote me on that. So in the long run, you have to make sure that you're entering the data properly and making sure that it's clean. Okay, so data cleaning is a process, and usually you can have groups of people working on this. So you'll have one person take a set of raw data and enter it into a spreadsheet, have another person take the same set of raw data, enter it into a spreadsheet, and then compare the two and make sure that they're the same. And if they're not, then you guys have to go back and look to see where the inconsistencies are and try and find out where the errors are. So data cleaning ensures that, one, your data is valid. Okay, so you want to make sure that it falls within the known ranges and conditions. So for example, if you're measuring people's height, okay, so you can have a little kid, who's like a foot tall, right? You can go to the tallest person that we know of is 8-9 feet tall. Okay, but if you all of a sudden come across a number, it's like this guy's 100 feet tall. That's outside the normal range. Okay, no one that I know is 100 feet tall, not even close. Okay, so you want to make sure that your data is a valid data entry. Okay, so usually there's going to be upper and lower bounds, which are what is acceptable. You want to make sure that you're within those bounds. Two, you want to make sure that it is accurate, and not just precisely measured. That's a different aspect of accurate. What I'm talking about is you want to make sure that it is the correct and exact form and the right type of content. Okay, so if you're looking for the speed that the car went by, and you look in that column and it says banana, that is the wrong form of the data. It's the wrong content. It is a string value, it's not a measured value. Likewise, if you're looking at the value and you're measuring it, and it says that the person's going 100 kilometers per hour, and everything else is in miles per hour, again, that's still the wrong form. It's the wrong units, okay? And I'm sure that in any one of your science classes, you always have your TA or your professor or your instructor harping to you guys on units. There's an example of I think it was the first Mars probe that went up, and they were trying to land it, and whoever the engineer was didn't convert from imperial system to metric system when he calculated out the speed and thrust when the thing was supposed to be landing on Mars. So this $1 million probe just barreled straight into the surface of Mars and exploded, and that was the end of that project. Right? From a simple, unit conversion problem. Okay, so the next thing you want to have, you gotta have it valid, you gotta have it accurate, you want to have it complete. Okay, so if you have, say you're doing an experiment and you want to figure out what it is, how body mass index affects your IQ. I don't know, that's a completely ridiculous experiment, but let's say that's what you're doing, and you've measured everyone's height and their IQ. Okay, you can't solve your problem now because it's not complete. You're missing their weight. In order to calculate a body mass index, you need to know both their height and their weight. Okay? Not just that, you gotta make sure that it's complete across the board. For the most part, you wanna try and make sure that it's complete across the board. So for every participant in your study, for every point of data, you have to have all the measures. Okay, so if you have a study and you have 20 people in it, but you only have the height measurement for 5 of them, then you're really not gonna be able to answer your question. You gotta make sure that it's complete. And in some cases in the real world, you're gonna end up in situations where 9 out of the 10 you have all the data, but that last one you're missing one of the values. And it's like, well, how do we handle this person? And they may have multiple measures associated with them, 15, 20, 1,000 measures associated with one person, but you're missing one of them. Do you throw that person out of the experiment? If you can afford to, yes. If you can't afford to because of time and cost, you may have to figure out a way around the fact that you're missing one of those values. For example, you saw there in the vector type coding, you could do sum and one of the values was NA. That means you don't have that one measure. And you type in sum and it says I can't give you an answer. But then if you type in that specific command where it says ignore the NAs, then you can get the sum for the remaining values. So there are ways around it, but you don't want to cut corners too much, or you don't want to do that with the majority of your data. Maybe 1 or 2 points is you can get away with. Consistent, you want to make sure that your measures are equivalent across all systems. This comes back to units, making sure that they're the right values, okay? Making sure that they're expressed the same way. Some people like to write things long form with all the digits. Some people like to write it in scientific notation, okay? In that case, you want to make sure that it's consistent across your measure. Other things, for example, everyone here has taken the survey at the end of the year, which is how satisfied are you with your course? It's like very dissatisfied, just satisfied, I couldn't care less, then it's like satisfied and overly satisfied, right? You circle them. And when it gets coded into the sheet, it's usually like 0, 1, 2, 3, 4, and 5, right? So it's a number, you can assign a number to it, but the term can also be used. So in some cases you may have measures and it's like 0, 1, 5, 5, 5, 5, 5, very dissatisfied, 5, 5, 5. You have to make sure in order to analyze it that you convert that one string or that one section of words into the proper number. So you gotta make sure that it's consistent. And then uniform, again, I'm harping on this again, same units of measure in all systems. Okay, so that's not just saying in one column. In one column for, say, speed, you have miles per hour. But then if you're measuring race times or something, the measuring in the race times in seconds. Now when you start to do manipulations and stuff, up to the time times the velocity, to try and figure out distances and so forth, if one is in seconds and the other is in miles per hour, when you try and multiply them, you're going to get gobbledygook answers. So you want to make sure that all of your units are in some way accounted for throughout your whole system. If you have a set of data that meets all of these criteria, then it is of the highest quality and you call it high quality data. If it's for the most part, if you're missing a couple points, you usually call it high quality data. Anything less than that, and it's just a bunch of data that's incomplete. So this is the standard workflow when you're going through a set of data. So you usually start up here. You've collected your data, you import it. A lot of the times, you're going to be out measuring height and weight, and you're going to be out measuring financial information, and you're going to be measuring something else, their purchasing power. You're going to have different spreadsheets, different groups of data, but in order to do your study, you need to have one cohesive set of data that you're going to work with. So you have to merge the data sets. You have to make sure that subject A has all of their measures across the board in that one set of data. So you got to make sure that they line up properly. And once you get out there, you can always have the best intentions of making everything look nice and neat and tidy, but when you're getting stuff from different people, it's always going to be in different forms. And the person who's responsible for analyzing the data is always going to be the person that has to manipulate it so it's in the right way so that everything lines up properly. If you're missing some data, there are techniques in which you can rebuild the data. One, you can just treat it as an NA and ignore it. Other times you can, if you're dealing with a large population, you can maybe replace the value with an average. Or if you're measuring something but it comes up as below the lower limit of detection, so you can't detect it, you did measure it, so it's not a missing value, you measured it, but it's below the lower limit of detection. There's specific values that are recommended by the instruments that you're using to fill in those blanks with. Okay, so you can rebuild the missing data so you have a complete high quality data set. Sometimes you need to standardize the data set. You want to make sure that it's of the correct form. Okay, so for example, if you're trying to compare, what's a good example? I don't have a good example. So for example, if you measure some sort of protein, it may be measured in nanograms per milliliter, but you measure another protein and it's measured in kilograms per milliliter. Well, kilograms is too large, but let's say, so nanograms to milligrams per milliliter. So there's like a million-fold difference between those. Now, if you wanted to say, well, this increased by this much in nanograms and this increased by this much in milligrams, did they increase the same amount? And obviously this one increased a little amount, but if you talk about the original concentration, how much it increased versus this one, you gotta put them on equal footing somehow. So you standardize it so that they're all on a comparable footing. Okay, and I'll get into that in a little bit. Normalizing the data means that the data should have a regular normal distribution. So in statistics, when you say something is normal, it follows this nice bell-type curve. It's even on both sides. You have, in the middle, you have what's normal, and most things are normal. Then you get deviations, but you get less and less deviations as you go on, and you get things that trail out. Okay, so it's got this nice bell-shaped curve, a Gaussian curve, a normal curve. Almost all statistics that people will be using is based on the fact that data should be normal in nature. Okay, it should be this normalized distribution. If, however, you are measuring data, and this happens a lot in biological data, is that it's not a normal distribution. It's skewed to the left. So you may have something that's got this long tail and then spike up and drop down. Okay, so it's all shifted to the left, or it's shifted to the right in one way. And then before you can do your statistics, you have to normalize it using some sort of transform. Okay, so that I'll get into that in a little bit as well. Deduplicate, again, because you may be dealing with groups of people that are giving you data. Some people may have measured the same thing twice, or you may have redundant variables that, for example, if you have speed and time, or sorry, if you have distance and time, you don't need another measure of your velocity or your speed. So if you have distance and time, you can calculate out the speed. Or if you're only interested in speed and you have distance and time, you don't need both of those, you just need to calculate out the speed and then go from there. So you may have groups of data that are redundant or duplicate in there, and in order to save on space and memory and so forth, you may want to get rid of those. So get rid of those. Verify and enrich, this is where you go through the process of making sure you have all the data again, making sure that everything's there that you need, making sure it's of the highest quality, and then you can export the data to go do various things with. And then that data will be exported, the stuff that you export will be imported by someone else, and then they'll have to go through the whole process again. Okay, and it can keep going around and around and around. And usually where the breakpoint is here between the export and the import. So usually a given project will start from an import of data and then an export of data at the end, which is your final results. But then you publish those results and someone else takes those as their initial input, and then they start their own study. And that's how science progresses, building on the backs of others. Now, like I said, I wanted to talk a little bit about this standardization and normalization of the data before the statistics. So, sometimes you need to apply these things that are called transforms in order to get the data in the right form. Okay? So for example here's a plot of the area, a person's living area, an area of space and what the population is in that area. And you can see here that it looks really gross. It's all clustered down here in the bottom corner. But you do have a few stragglers up here that are way up at these really high values. And you really can't figure anything out in here, okay? But if you take this and you put it on a log scale, so here's the log of the area, and here's the log of the population. So the transform that you're applying is you're applying a logarithmic transform to the data. You take the log 10 of all your data, both your area and your population. You can see that there's this nice, almost linear trend between the two, okay? So now you can see the relation between these two things. Here you can't. Here it's just a mess. But now you apply the transform, and now you can start to see the pattern a lot easier. And you can start applying the statistics a lot easier. So there's different types of transformations. So standardization, like I said, is if you're trying to compare something that changes like this versus something that changes like this. If you want to put everything on equal footing, what you can do is something called a Z transform. And basically all that does is it takes your value, you minus off the mean of of all the measures that you've taken for that one value, and then divide it by the standard deviation. And what it does is it takes that data, which may have some mean and some standard deviation, and if you apply that transform to it, what it does is it takes it so that the mean of your data turns to 0, and that the standard deviation goes to 1. And you can do that with all of your data, so every single set of data will have this same distribution, okay? And then when you compare between groups now, you can also compare across different measures that normally wouldn't be allowed to be compared because they're on different scales and so forth. Here, this is what's known as a skew. So everything here is skewed to the left and skewed down. Okay, so if it's skewed to the left or skewed low towards the low end of your scale, if you apply a logarithm, that's where you can spread it out. So normally in biological data, you apply a logarithmic transform to spread it out. If you have the opposite problem and everything's skewed high, then what you want to do is the reverse of a logarithm, which is taking it to a power. So you can, a root. So you can take a root of the value and you can drop it down to, that might be the case. I'm not sure if roots skew the same way as logarithms or not. I can't quite recall. But either way, taking the root, so they're taking root 2 or the root of all your values, the square root of all your values or the cubed root, or raising your values all to a given power, so square all of your values and so forth. You can change the skew in one direction or the other. I apologize, I don't quite remember which way is which. Then you can also try and equal the spread or the, so for example, you may want to compare men versus women in a given measure. Now, because men are usually taller and heavier than women, if you're doing anything with weight and size and comparing men versus women, sometimes what you need to do is you need to skew all of the female data so that it lines up with the male, or conversely, skew all the male data so it lines up with the female data. And there may be some sort of linear transform that you can apply to get the two to kind of line up so that they're, again, on equal footing. So you can compare men versus women. And I mean, that's one example. Okay, so once you've done these transforms, you've got your nice high quality data set, everything's in the right form, you can do some statistics on it now, that's when you can start going and doing a little bit of exploratory analysis. Okay, so you can look at it and say, well, what kind of things can we determine from this data? So you can do a little bit of descriptive statistics, some data visualization, and from this initial exploratory analysis, it might tell you a little bit of information that may cause you to do more analysis, or it could lead back to, oh, we need to go back and put the data in a different form before we can proceed with more analysis. So descriptive statistics, I mean, statistics is a whole world. Is anyone here in statistics, by any chance? You're taking statistics? Does anyone want to become a statistician? Maybe? Maybe. Okay, so there's different ways of analyzing data. And once you get into the deep, dark world of statistics, there are many, many different ways to analyze things depending on what it is you're trying to answer. And a lot of the statistics hold only for certain ranges and criteria. Okay? So for the first type of, the stuff that you're going to be mostly familiar with is called univariate statistics. So there's one variable that's usually involved. Okay? One independent variable. And there's two classes of statistics. There's statistics that are based on parameters, okay? And then there's statistics that are based on ranking. Okay, so there's parametric based on parameters. So what are the actual values that we're looking at? Whereas the non-parametric is based on how you rank the data in a given order. So if you rank it from highest to lowest and do that for your measures, how does it rank compared to between two groups? So examples of parametric univariate statistics are the student's t-test. And who here has done student's t-test or knows what I'm talking about? All right. This is a basic test to determine if the means of two groups from two normal distributions if they can be considered statistically different or not. So if you're basically, this is like your bread and butter for statistics for the most part.
Yeah, guys, there's a lot of murmuring, so that means you're not paying attention. And if you can't do a t-test, you're not going to be able to analyze half of your data. So this is really not a time to be doing other things.
If you have more than, another way of doing it is a one-way ANOVA. Okay, so if you're only using one variable, then a t-test and a one-way ANOVA are almost identical. Non-parametric is where you're not looking at the actual values, so how different are the two means, but what you're looking at is how does the ranking of the data change. So when you look at the ranking, are these things coming from the same groups? Can you say, are they part of the same ordering? So things like the Wilcoxon rank sum test, which is the equivalent, the non-parametric equivalent of the t-test, and the Kruskal-Wallis test, which is like the non-parametric version of your ANOVA. Now, if you start to get into more variables, you can do two-way ANOVAs. Okay, so it's dealing with multiple variables. So now you want to know, how does height change in response to weight and gender? Okay, so now you got two dependent variables with one independent variable. Okay, so that's part of more getting into multivariate. As well, you can get into things like regression, principal component analysis, correlation analysis, and more fancy statistics, which I'm not going to get into too much. Now, the nice thing about these programs is that a lot of this stuff is built into the program. Okay, so you just have to know what the syntax is and say, I want to do a t-test on values and absolutes. You know, between the two groups, what's the difference? Are they from the same distribution, yes or no? And you just type that in and hit enter. If you're doing it by hand, there's all these calculations and you're writing it all out. You have to do a lot of serious math behind it. But because software has taken away a lot of that, you really don't need to go into a lot of the statistics detail in order to use it. That being said, you should understand the math that's behind it. So unfortunately, it's good in one way that anybody can sit down and run a software program to run statistics. So it just puts our statistical ability up through the roof on the good side. On the bad side, anybody can run statistics, even if they don't understand what they're doing. Okay, so you might be using the wrong assumptions, and you might run some statistics and say, look, I found something significant, but you're using the wrong type of statistics and so forth. So it's what's a Spider-Man thing? With great power comes great responsibility. Okay, so when you're doing statistics and people are relying on you to determine certain things, you should try and make sure you know what you're doing, because you're going to be giving them answers and they're going to be basing decisions based on what you tell them. Okay? They don't have, and just a quick aside, when I first got into the workforce, the thing that shocked me the most is that I would do something and then I would tell the person, well, this is what I found, and then they would just take it and run with it. There was no teacher that was looking back and saying, yeah, you did that right, or yeah, you did that wrong. They just assumed I knew what I was doing, which was the scariest thing in the world. It's like, is someone going to figure out that I'm doing something wrong? I think I'm doing it right, but no one's there to correct me. So when you actually get out there, they're just going to assume you know what you're doing and hope for it, and they don't have time or the resources to do your job as well as their job. That's why they gave you the job. Okay, so make sure you know what you're doing when you get out there. A lot of these packages in R are predetermined, so you just have to go to R and you can download a lot of these programs and you put it into your R program, and then now you can do things like t-tests, and you can write t-tests and then tell it to do what it's going to do, and it'll work it out for you. So for example, here, this is exactly the syntax. T-test y to x. Okay, so if you have two variables, you can throw it in there and figure out what's going on. Now, that being said, after you run some statistics, nobody wants to hear about statistics other than if it's significant or not. That's about it. So when you go and you're going to go give a presentation to, donors, funders, your boss, the board, whatever it is you're going to be working with, they want it to be nice and succinct and clean and easy to understand. And that is the hardest part of the job, is taking the complex stuff that you guys do and making it simple so that anybody can understand what you're talking about. And visualization goes a long way to showing you what's going on. So here's a nice graph of the weight of automobiles by origin. Here's the weight, here's the origin, and then you have these nice little graphs here. So in the old time, you might just put a bunch of dots on there and kind of eyeball it. Over time, you can develop things like the mean, which is this blue bar. I think it's the blue bar. The median, which is the red dot. You know, the upper and lower quartiles of it, the standard deviation, and all that information is now included on a single plot. And once you understand how to read that, it's like, oh, you can see what you're looking at here. And so now you can easily look at it. So say, look at, well, the USA makes the heaviest automobiles, and Asia makes the smallest automobiles, right? Is it significant? That's the other part. You can look at that and say, yeah, it looks like they make heavier automobiles than the Asians do, but you have to go back and do your statistics. Is it statistically significant, or is it just a flub from the numbers that you've collected? Maybe it's a random chance. So if you have something statistically different, usually there's a star or something highlighted to show you that it is different. Again, here's another graph looking at real estate sales by volume over year, depending on the value. So you can get these complex sets of data, but you're trying to condense it and make it easy to look at. And here's just a simple scatter plot, where if you plot it, just even plotting your data, you can see that there's some sort of quadratic or quartic trend there that you could take advantage of. Okay, so usually the very first thing I always tell my students when you're doing exploratory data, before you even get into statistics, just plot your data and look at it. Just look at it. Say, oh, you'll be able to see, is it all clustered in one corner? Do I need to apply a transform to it? And then you go back, apply the transform, and then you do it again. You plot it, and you look, and you can start to see. And what you may find out is you may get, clusters, a group of things down here versus a group of things up here. And you might find that you have two distinct populations that you're looking at. You can even get into more complex things like, this is like gene expression data coming along here. So points versus points is a correlation map. So what are the things that are correlated with one another? This is a network map. We use this a lot in our lab. And you can look at the relation between multiple biological markers all at once. So that's what we do. And so you have these nice networks, and you can see what it is that is interacting with itself. You'll also see those kind of graphs when you're talking about social networks. And you'll find things like, this person here is very important because tons of people are talking to them, whereas this guy's over here, he's got no friends because he's not talking to anybody, right? So that kind of information can come out just from looking at the data. Okay, so that being said, once you have your data, the meat of what you guys are going to be doing is the statistics, as well as learning how to look at the data. So one, how to analyze it, two, how to present it. Okay, so for the next little bit, why don't you go through chapter 4? This will be going through the summary statistics. So this is how you do some statistics using R. So this is probably an important chapter, so I'll give you guys about 15 minutes to work on that. Is there any questions, by the way, as we're going on? Feel free to just stick your hand up and ask as we go. Okay, so once you've done some initial exploratory statistics, you kind of figure out what's going on with your data set, then you can go to full scale processing. And for the most part, I mean, if you're really getting into data analysis, if you're really into research analysis, there's processes that you're going to be doing over and over and over and over again. And either A, you can do them over and over and over again by hand, and it becomes really repetitive and really boring. It will guarantee you a job. And then there's a lot of people that are out there and they do data analysis and data entry, and that's their job. But over time, you can come in, once you start to learn kind of these programs, you can figure out that those processes that you're coding into, say, R, is you can write the program so it does it automatically over and over again. And now you've gone from just simple analysis to an algorithm. So an algorithm is a process that logically follows through a group of steps. Okay, so you can tell the computer, do this for all the data in this file. Okay, and then you're going to get even more complicated. Do this for all the data in the file, and if this answer is greater than X, then do this process. And if that process gives you another value, then do this process. And you can start to, code and make things more complicated, and you can start to build more and more and more into either your model or into your algorithm. Okay, so after exploration and cleaning, you can build models and algorithms to produce your desired measures. For example, you can do things like classification models. So how is it that I can distinguish two groups from a set of data? Okay, so high spenders, low income, low spenders, high income, that kind of stuff when you're looking at financial data. So you may want to look at the data. You have a different number of measures, but you want to break them into groups. You want to cluster them into groups, and that's known as clustering analysis. You can do other things like machine learning. So you're looking for patterns in data, okay? And this is what's used a lot in things like Amazon or Facebook. They're looking for patterns in the data such that, a given group of people that buys X, Y, and Z tend to buy, W. And so if you go on there and you start to buy X, Y, and Z, then all of a sudden an ad comes up for W because they know that people that tend to buy those things also tend to buy this other thing. So you can start to come up with some sort of process that learns what the pattern is in the data and then maybe enacts a certain outcome. Or you can use an algorithm to break groups of data into different categories. Okay, so other things that are more common are things like linear regression models. If I want to describe, 3 or 4 variables, or learn how 3 or 4 variables affect one final variable. For example, if you have 2 measures, and you can see that there's a nice linear trend in there, and you put a nice line on that, then you can start to describe your y variable in terms of your x variable. That's a nice linear regression, but you can do this with higher order measures. So you may have 10 variables that you can use to describe one final outcome and so forth. And then otherwise you can do things like correlation analysis. So we may find that it's correlated that those people that tend to work 9 to 5 are also the same type of people that have kids, car and house. I mean, that's not a good correlation, but there may be that kind of information in the data set. And you may be looking for a specific type of a person or a specific relation that you can take advantage of either for financial gain or for marketing purposes or to discover new things in science or whatnot. So whatever field you're in, this can be useful information. So a clustering algorithm is something that looks at data like this. And clustering itself is a subset of machine learning. It's an unsupervised machine learning. So you just give it the data. So here's 2 variables and there's some sort of pattern there. And you say, what are the main groups that I can find in here? And you don't tell the computer anything else. You just say, I want to know what are the tightest groups in here. And you can kind of see that there's like a little bit of a group here and a little bit of a group here. But it applies a specific algorithm to it and it starts to pick out the data and it would cluster it based on this. So you've got 5 or 6 different clusters of groups based on these two measures. Okay, and then these could be different populations that you now want to analyze. So here's cluster A, here's cluster B, and maybe you have some other measures down the road that now you want to look at the difference between cluster A and cluster B in other measures. So we do this a lot with patient data. So we look at a group of symptoms, so you can take this variable and this variable to be symptom data. Okay, and you want to say, well, in this group of people that we know are sick and have a specific illness, are there subgroups in that illness? So maybe you have an illness that's like, say, Parkinson's disease, okay? And some people may have more problems with their gait, okay, and the way that they walk, as opposed to some other people who have problems with their speech patterns or their facial expression patterns. And underlying all of that, you could expect that there's some sort of biological differences. So you can cluster your data based on symptoms, and then once you know what the groups are of the symptoms, now you look at their biological data separately and compare it to find out what the differences are. And then maybe you can find what are the biological things that are giving rise to those specific symptoms. Linear regression is trying to apply, like I said, some sort of relation. So here, here's some sort of measure here on the x-axis. You got a measure here on the y. I can't really make it what that says, unfortunately. But here you have this nice linear relation. So now, if you have this strong linear relation, anytime you measure this, you can automatically figure out what this is. Okay, so maybe this thing is really cheap to measure, this thing's really expensive. Okay, so if you can figure out what the relation is, and now you can start to save your company money, or you can save your lab money, or whatever it is that you're doing, because now you can relate these two measures to one another. Or maybe this is like dirt easy to measure, and this is like really complicated. Usually that goes along with the money too. But if you have that sort of relation, now you can cut out the measurement of one of your variables and apply the relation to the two. Here's an example in terms of different dimensions. So now here you've got two variables that you can measure, which describes a third variable. And here, instead of a nice line, you have a plane. Okay, now if I want to describe this, I just have to measure these two coordinates and then apply the relation there. And you can think of that in terms of more higher order measures. So maybe the thing that you're really interested in is super difficult to measure, and then there's like 5 or 6 easy things to measure. But if you can figure what those 5 or 6 easy things are and apply a relation, you can get around the problem of trying to measure the final product. Okay, so that's just a quick, simple examples of things that you can apply. So there's basic statistics, which are just looking at difference between the group, but then there's these more complex things of finding relations or building models based on the data that you can then apply in some sort of algorithmic process over and over again to give you more and more data. Now, after you do this kind of final data analysis, this complex data analysis, then you move on really to the final thing, which is your product. Okay, so initially you set out to do something. Okay, you're given a project to answer a question, to test a specific hypothesis, or you're given a project by your boss to figure out how to save the company money, and so forth. Once you've done all your analysis, you've collected the data, you've done your statistics, cleaned it all up, done your statistics, figured out some sort of process that you can run over and over again. So now it's really easy to do it from this point forward. You come up with your final product. So either the product could be just the answer to the question, which is, what's the relationship between age and height in an elementary school? Or it can be a code or an algorithmic process or some sort of model. So you can come and say, this is the relation and this should hold across all populations. Or here's an algorithm that you can now use. Anytime you collect data, you just put it into that and it'll give you the answer, and you no longer have to do it anymore. Okay, so it could be a model or algorithm or just a simple output. The aim for any sort of process, algorithm, or model is to make it as automated as possible so that you can repeat the process ad infinitum, which means just repeat it over and over and over again. And basically, it's taking the work out of a human's hands and putting it into the hands of the machine. And the reason you want to do that is because humans make mistakes. Okay, there's always going to be errors, and then your data becomes poor quality and you can't trust it anymore. But if you can build a process that you can do over and over again, now you have this little chunk of analysis that you can use, and then you can use it, and then you can use it, and that's everything that's going on in technology with computer science, and in any field, it's building these algorithms on top of one another to take advantage of them. Okay, so if you wanted to look at, say for example, computer science back in the 40s and 50s, they had computers back then. They were very simple, and they had cards of paper with holes punched out into them, and they'd have to go and they'd feed them into machines. And that might have been in the 60s and 70s, and they would read these cards and then go through, and if you messed up the order of your cards, it would be a problem, and you'd have to throw it all out and start over again. Over time, they automated that process, and they made the computer do it itself, and they kept building on it, building on it, building on it, and building on it until you have little tiny phones in your hands that can do more than any 1950s computer could ever dream of doing. Okay, and everybody has these now. Okay, so that's the idea. You keep building on it, and from this point forward, everything is going to keep building on previous stuff. And it's going to get more complicated, more, I don't know, more something. I don't know where it's eventually going, but it's going somewhere. Then finally, now you have this beautiful product. It works, you've tested it, it holds, it can save your company money, it can make you rich, it can solve a scientific problem, it can solve a health crisis, whatnot. Now you got to tell other people about it. You got to be able to communicate it. Because just because you have an algorithm that works doesn't mean that you can make other people understand it. Okay? I've been up here for the last 2 hours trying to make you guys understand everything. I don't know if I'm getting through, but I'm trying to do my best to communicate some of this stuff. Okay? When you build and work on something, you get into this headspace where you get it. It's like, oh, it's so obvious, it's so easy. Then you go and try and talk to someone about it, and they have no idea what you're talking about. Okay? So this is actually the most important part of the product, because you have to be able to convince other people of why it's important, why they should use it, why you spend all their time and money on building it. You're never going to be able to show them everything. Okay, there's way too much information. Okay, so you have to be able to distill what it is you've done into a few coherent points that will convey your message. Just the bullet points, the highlights. Okay, and then emphasize this usually in a way that can be visualized, because people just like looking at pretty pictures. Right? This will be dependent on the user, and when I say user, this will be dependent on your audience. Okay, so are you talking to your grandmother, trying to tell her what it is that you do all day? Are you talking to the head of the board? Are you talking to a new recruit? Are you talking to someone who's an expert in the field who developed the kind of algorithms that you're working with? It's going to be different levels of complexity depending on who you're talking to. And above all else, whenever you're trying to think about describing something, always try and think of it in terms of what they call the elevator talk. So I call it the grandmother talk because I prefer talking to my grandmother than people in the elevator. But if you get in an elevator, from the time it takes you to go from where you got on to get off on your floor, could you explain to someone what it is that you do? Or what it is that you did to the data? So I collected data on Alzheimer's patients, and I just checked to see if age has an effect on inflammation in the brain. Right? It sounds very simple, but years and years and years and years of work. Okay? Or you can think of it, I like to think of it in terms of talking to my grandma. You know, Grandma, this is what I do. You know, you have absolutely no idea how the computer works, but I work with computers every day, and I try to explain to her what it is that I do. Okay, so simple, but conveys all of the information. Okay, and with that, this is what, I'll just highlight this and tie it back into your programs here, this is basically what your poster is going to be at the end of your work term here. Okay, so you want to be able to discuss what it is that you've done in a simple enough way that people walking by can look at it and kind of get an idea of what it is just by looking at it, but not so much detail that you overwhelm them, and it's a very fine line. Okay, you'll find out if you've ever, who here has been to a poster presentation before? Okay, well, the one thing that you'll find is that when you're walking around, you look at posters and some of them are like, I don't care what that says, I'm not going to read it, because it just looks gross. And other ones are like, wow, that looks awesome. I don't know what it says, but it looks awesome, so I'll try and figure it out. And then there's like the holy grail of posters. It's like, that looks amazing. Oh, I understand everything they did. I could do that. And then you actually try it. It's really difficult. But that idea of making it seem so simple that anybody could do it, that's what you want. Because then people will talk to you, how did you do that? And then you lure them in. Right? And then they have to listen to you talk forever. Okay, so that's the end of my presentation. I know we there are a couple hiccups along the way. Does anyone have any questions about any of this stuff? I know it's kind of like a gross glossing over of the field, but it's an introduction to data analysis. I hope you guys got a little bit of a flavor for what kind of skills you would need to do to become a data analyst. A little bit of programming, a little bit of common sense on how to organize data and so forth. If you have any questions, feel free to talk to Dr. McGolan, or she can refer you to me if you have anything that you want to ask me specifically.
Do you have your contact information on one of the slides for them?
I don't think I do. No, I don't, unfortunately.
If you do have questions about data analysis, you can contact me for Dr. Paddock's information. Your best resource will be your own mentors because they will know exactly what type of analysis is best for your study. Depending on the kind of work you're doing, you might want to do ANOVAs, ANCOVAs, PCF, whatever it is. Depends on what you're trying to study. So please make sure you talk to your mentors. Before you go, please remember, mark your calendars if you have not already. Your next workshop will be the poster and abstract workshop. I've had a number of people tell me they're starting to work on their posters already. That's awesome. But the workshop will be the 24th, which is 2 Mondays from now at 4 p.m. Not 6 p.m., 4 p.m., room 2151 with Dr. Patton. Please come ready to listen. He has really entertaining information on what's going to make your poster be the holy grail of posters versus the solid block of text that everyone's going to walk right past and shield their eyes and not make eye contact with you. If you have questions, I'm here. Samantha's here. Regine will be back any moment. If you have a red chair or a blue chair, if you can bring it out to the back to make it a little easier for the cleanup, we would appreciate it. Have a good night. Thank you for sticking around.